The third approach of accounting for risks and cost-benefit analysis is called Monte Carlo simulations. So here, each variable has a probability distribution, and each variable is linked by an equation. For example, one item of benefits could be the output produced by the project, so which is equal to quantity times price. And suppose we have uncertainty on both quantity and output associated due to this project and the price of the output. And we know that the quantity output has a distribution of this, and price of the output, the product, has a distribution of this. Then quantity times price, we get the benefit. It has associated distribution of this. So from knowing the distribution of quantity and the distribution of price, we can construct the probability distribution of the benefit. So probability distribution are constructed for all other components of NPV calculations, like capital cost, unit cost, length of project, discount rate. Well, in practice, not all other cases. For example, we might know the length of the project for sure. Then we don't need to account, or there's no risks on the aspect of length of the project. Then use a computing programs, for example, like Excel, with which samples from each distribution and calculates the NPVs. And that's done many times to obtain the probability distribution of the NPVs. Then decision is made using expected value and the possibly the standard deviation of risks. So then make decision regarding the using the expected NPV and the risks standard deviation. Okay, let's continue with the examples that we had previously, and let's handle risk by Monte Carlo simulations. So we know that the project has a fixed cost, which is $500. Unit cost of $2 per unit. And suppose we know this for sure, so there's no uncertainty. Number of the length of the project is 10 years. Discount rate is 10%. And quantity per year, and let's assume that we know it for sure is 100 units. However, we have uncertainty regarding price, which we don't know exactly what price it's going to be each year, but we know is probability distribution. So we have there's a risk associated with price of the output, but we know it is uniformly distributed between $5 and $20. All right, and so we want to use Monte Carlo simulations to account for these risks. So what we want to do is we're going to draw from this uniform distribution between 5 and 20, say 1,000 times, compute the associated NPV, and then find what's the expected NPV, what is the standard deviation, which measure the risk associated with this project. Okay, to do that, previously we know that the cash flow patterns, that this is a 10 years annuity factor. This is 10-year annuity Okay, so we want to calculate the present value of this 10-year annuity. So let's calculate annuity factor first. So which is equal to 1 minus 1 plus I, so which is B5 raised to the power of negative n, so which is B4 divided by I. B5. So that's the annuity factors. Let's set using 2. Okay. So now let's draw a price and compute the associated NPV. So I'm going to draw the price from the uniform distribution between $5 and 20. So we go to data analysis. Run the number generations. Then okay, I'm going to generate only one variable, which is price, and I'm going to generate 1,000 of this price from uniform distribution between 5 and 20. Output the results starting from this. Okay, so that's the possible. For example, the first draw would be $16.16 something. So let's calculate the NPV associated if price is at this level. So NPV would be equal to this is 10 years annuities, so it's per year payment, which is quantity 100 times price, which is A11, take away the unit cost B3, and times, so this is per year cash inflow, and times the annuity factor, so which is B8 minus the fixed cost, B2. Okay, so if price is $16.16, the NPV is around $8,200, and do it for all levels. Now we have this 1,000. We have 1,000 draw of the prices and compute 1,000 associated NPV. So now let's calculate the mean and the associated risks. So again, we are going to use data analysis, descriptive statistics here, input range is here. Okay, that's the data. And I'm going to ask Excel to compute the summary statistics and output the results to say to here. Okay. So the mean here is average is $6,184.70. The risks is the standard deviation is $2,640. Okay, we can also draw the histograms of the MPVs. So to do so, let's first create bins. So let's look at the minimum value is 1,351. The maximum value is 10,000. So the bin is this. Let's use these two bins. You can choose other bins as well. So basically, Excel will, okay, we are using this bin. Excel will count how many of this 1,000 MPV we calculated has a value of less than or equal to 2,000. How many is between 2,000 and 4,000? How many is this, so on and so forth. Okay. So let's look at data analysis, histogram. Input range, that's the data we have. The bins, that's the bin we have chosen. I'm going to ask Excel to draw a chart and output the results into, say, here. And okay. So we see that that's the histograms. The distribution of the MPV. We know that the price is uniformly distributed. However, the MPV is not that so uniform. So the problems with Monte Carlo simulation is that deciding on the probability distribution for the variables. For example, like in Excel, why the price distribution is uniformly over $5 and $20. Okay, and that's something we may not know. And it is also difficult for the client to change the assumptions because it is built into the computations. There's no degree of freedom for the client to change it. And it's difficult for clients to understand as well. So it's not that intuitive. The fourth approach to account for risks and cost-benefit analysis is called loading the discount rate. The idea here is that, okay, since we need to discount the future benefit and cost back to present times, why not account for risks in the discount rate? So here the discount rate is increased from the base level risk-free rate, for example, like a treasury bonds rate, to reflect a given level of risks. An example is, if the bond rate is 4%, which is risk-free, and you are considering a low-risk project, then you might use a discount rate of say 6%, which is just 2% over the risk-free rate. In contrast, if the project you are assessing is risky, then you might use a high level discount rate, say 12%. Here are some problems with this approach. First, it assumes that risk grows exponentially over time. Okay, so when we discount, it's exponential discounting. Okay, so since we handle the risks, we augment the risks, we augment the discount rate with risks, then we are actually assuming that the risk is growing exponentially, and in reality, it might not be the case. And we are also assuming that government should act in a risk-averse way. Well, this might not be true if we are thinking that the government should be risk neutral. And such kind of risk loading usually reflect total risks rather than the systematic risks. So systematic risk is the risk that cannot be diversified away. Risk that can be diversified we call unsystematic or idiosyncratic risks. And total risk is the sum of these systematic risk and idiosyncratic risks. And this is wrong according to the capital asset pricing models. Okay, anyway, this is the fourth approach to account for risks and cost-benefit analysis. The fifth approach is called certainty equivalence. The idea is to ask, okay, given the risks of benefit and costs in the future, what's the certainty equivalent amount? And let's use this certainty equivalent amount of benefit and costs in computing the NPVs. The certainty equivalent of an offer of a given number with uncertainty is how much that offer is equal to with certainty. For example, if you consider that in the offer of $100 with a probability of 50%, which means there's a 50% chance that you will get $100 and a 50% chance you will get $0. If you can consider this lottery is equal to $70 with certainty, then you are going to use this $70 in the NPV calculations. With these measures, you convert all variables to their certainty equivalence and calculate NPV as usual. And we have the similar problems as the fourth approach.